Okay, we're in section 6.4, circuit analysis of AC resistive circuits. AC circuits composed of resistors can be analyzed using Ohm's law and Kirchhoff's law, just as we did with DC circuits. Care must be taken that correct formulas are used for peak voltages and currents, average voltages and currents, RMS voltages and currents. And typically, power ratings are RMS values in an AC circuit. Okay, with that introduction, the rest of this session is going to be purely circuit analysis and calculations. And we will start off with a little discussion about RMS and peak power. Here we have a circuit, and this is 100 volts. And let's see, let me make sure I've got my little pointer turned on here. This is 100 volts, and this is in RMS. Now, we're going, and remember this is an AC calculation. AC calculations concerning Ohm's law will be just the same as we did with DC. So remember we said that E over R equals I. So in this case we have 100 volts RMS divided by 10K, and if we solve for that we'd find that that equals 10 milliamps. And when we did power we said that voltage times current equals power, and we also said that voltage squared over R would also equal power. We could use either formula. At any rate, let's calculate the power. If we have 100 volts times 10 milliamps, we're going to get 1 watt. And if we took 100 squared divided by 10K, again we would get 1 watt. Now, this is the standard way that RMS power is calculated, and the reason is that, remember when we talked about the comparison of peak to RMS, remember we had a peak value, and we said that the RMS equivalent would be 0.707 of that, and that value represents the what the heat dissipation would be if it was measured in DC. So RMS is always a little bit lower than the peak. Okay, so let's consider what the power would be if we were evaluating this in peak. So first of all, we need to convert this to a peak value, so we would say 100 volts divided by 0.707, and that would yield 141 volts. So we're starting with a higher value, and so we're going to have a higher voltage or higher current drops. So we say again 141 volts, in this case divided by 10 k ohms, and we're going to have 14.1 milliamps of current instead of the 10 milliamps we had over here. And if we were to calculate power now, and if we said 141 times 14.1 milliamps, then it'd be about 1.98 watts. And so when you consider peak power, it is going to yield a much higher, almost twice as much than the equivalent RMS. As I said, RMS is pretty much the standard. Sometimes you'll see peak ratings with manufacturers of audio equipment, so they try to make their product look a little better. So be very careful when you evaluate the power on amplifiers and whatnot, because in this particular situation, if the say let's amplify it out 100 times, and so here you've got a 100 watt amplifier rated in RMS, and then there's another amplifier that says it's 198 watts, but this is in peak, and technically if you do the math, this is, they're the same power. So anyway, this is a discussion. This is related to RMS versus peak power. Okay, the next circuit we're going to look at is right out of your textbook, and we're going to be looking at this. In fact, we're going to look at this on 3 different screens. This first screen, we will evaluate peak values. Maybe I should write that here. This is going to be peak, and the next one will be RMS, and the final will be average. So this starts out with a 25 volt RMS voltage source here, and since we're doing peak, we need to first of all convert over to peak. So we would take our 25 volts divided by 0.707, and that would yield 35.36 volts peak. And since we have a combination of series and parallel here, we should evaluate the resistance of the two in parallel. So let's draw a little simplified circuit here, and we'll say this is R1 here, and then we'll have just one resistance here that represents R2 in parallel with R3. And so we need to do a little math here, and remember the calculations for parallel circuits. We would say 1 over, in this case would be 1 over 470 plus 1 over 680. And if we did this calculation, the resultant value is about 278 ohms, and this would be our equivalent simplified circuit. So if we wanted to know because one of the goals here is to calculate all the currents in these circuits, so we need to know what are the voltage drops at each point in order to do that. So given these two values, there's a number of ways we could do this. We could take the total voltage divided by these two components together, and we could get the total current, and then we could calculate what are the voltage drops. We could do it that way. Another way is to do a voltage divider, which is what I'm going to do, and we will say 278 divided by 278 plus 100, and this is just doing a proportion here to find out what proportion of this compared to the total resistance will this drop. And so in this case, the proportion here is going to be 0.735. And if we wanted to know the voltage drop across this component, and remember this is both these components, we could go 0.735 times the total voltage, which is 35.36, and that would yield real close to 26 volts peak. And so that would be the value across these two components. And we could use Kirchhoff's law to determine the voltage drop here. And remember, Kirchhoff's law says that the sum of the voltages in the circuit will equal the source voltage. So we know that the source voltage is 35.36. If we subtract out the 26 that's dropped here, that will leave what's left over here, and that's going to be about 9.35 volts, something like that. And so we'll have 9.35 across this component and about 26 volts across these two. So then we need to calculate the current drops. And so we now know we have 26 volts across this component, and we could calculate the current across this by simply taking 26 volts across 278, and we would know the total current. In fact, that would give us the total current through here, and that would actually give us the current through here as well. But we do need to know the individual current drops, so let's just use Ohm's law again, and we will say 26 volts across 470, and that's going to yield 55 milliamps. And then the same thing, 26 volts across 680 ohms, and that is going to yield about 38 milliamps. Again, we could add those together and that would give us this, but just for the sake of calculation, let's say 9.35 divided by 100, and that will yield, what, 93.5 milliamps. And if you add these together, you should get that. I did a little bit of rounding here, so you got the 0.5 there, but these two together is going to roughly equal this. Okay, so those are the basic calculations using peak. And remember, we started out with RMS, we converted to peak, we did the voltage divider here, and we calculated the voltage drops and currents in this circuit. Now, this was in peak. Your text does mention the values for peak to peak, and remember that, let's see, where can I draw it? Here's our, if this is an AC signal, remember the peak value is from here to here, and the peak to peak is going to be the from peak to peak. Okay, so the peak to peak is going to be double what we see here. So if we'd have done these calculations with peak to peak, everything in this circuit would be double what it currently is, except for this ratio right here. Okay, the next one we're going to look at, we're going to do the same circuit, only we're going to do it in RMS. So with RMS, we start out with the 25 volts. We do not need to convert. We can just go directly with that value. And let's see. Let's consider our equivalent circuit. We had R1, and then we had the parallel of R2 and R3 here. And let's see. We already did the the voltage divider. So let's just take our value, 0.735 times 25. And that is going to yield 18.37 volts, and that would be our voltage across R2. And again, if we used Kirchhoff's law and we took our initial 25 volts minus 18.37, that would yield our voltage across R1, which is going to be about 6.62, something like that. And that would be our voltage across R1. If we calculated our currents, let's see, we have 18.37 is our voltage across this leg divided by 470, and that should yield about 39 milliamps, and 18.37 across the 680 component would yield 27, and again these two together should equal this value. And so if we took let's see, 6.62 across the 100 ohms here, and that would yield about 66 milliamps, and so this would equal the sum of both of these. So this is the RMS calculations, and I skipped some of the things because we did them already in the peak calculations. Okay, given the same circuit and doing the average power, and again, I'm not going to do all of them. I'm going to do remember, first of all, let's talk about what the average is. Remember from a previous discussion, the average value is going to be 0.637 times the peak. And so in this case, remember we started, this is the circuit we initially started with, we're 25 volts. We need to convert that to peak, so 25 divided by 0.707, and that's going to yield the value, let's see, 35.36. So if we take the 0.637 times 35.36, we will get 22.48. and this represents our average voltage. Now, again, I'm not going to repeat all those calculations, but we would start out with this as our source as 2248, and we would just do everything the way that we had previously done it, calculating our currents, our parallel voltage drops, and all other calculations. We would just start with this value, 22.48. Okay, so in this lesson we have looked at AC analysis for resistive circuits, and we've looked at average. Then we looked at we looked at RMS, and we looked at peak. And at the very beginning we started out with a discussion comparing the RMS power to peak power.